Hello again, class. In this lesson, we will explore the connection between motion and force and understand what the different forces are that act on objects that are both at rest and in motion, and how we can represent those forces visually in diagrams. So remember that we're trying to explain why a small lightweight object experiences a different force from the fall of a more massive object, like a small ant can just walk away unharmed from after it fell from a great height. These words may come up today. We're talking about the mass, the amount of matter. Vectors are quantities with magnitude and direction. We can represent those as arrows in diagrams. Equilibrium is a condition in which opposing forces are balanced. And we'll be using the word net, which might be misunderstood as a net, but when we say net, we mean the total. And a law is a statement based on observations that's assumed to be true. So we're going to think of scientific laws, and remember the word perpendicular, which is 90 degrees to a given line. So we can represent forces as pushes or pulls, and a force can accelerate an object from rest into motion. If an object's already in motion, forces can cause the object to speed up, slow down, or change its direction. So a force can be defined as a push or a pull, representing from an interaction between an object and its environment. Friction is a force that opposes motion between two surfaces that are in contact. So the box, if we want to push the box, I can push it a certain way, but friction against the surface it's resting on will stop it from moving after I stop pushing it. So these forces can describe what's happening in the image, the force applied to an object by another object. If this is an applied force going this direction, we would say that's, I just said it. So this one would be applied force. So I want you to think, is it applied, a normal force, the force of gravity, or the force of friction? Okay, so the force acting opposite to the direction of motion when two surfaces are in contact with it, the force pushing this way would be friction. The force of attraction between the mass of an object and the earth, the force of the earth pulling on objects is gravity. And the force acting on a surface in a direction perpendicular to the surface, we see the table pushing against the box, is called normal force. It's perpendicular, so this is always at a 90-degree angle with the surface, whether it's a ramp, it would still be a 90-degree angle here. That would be the normal. The normal force is the force acting on a surface in a perpendicular direction. So this one's called the normal. The road is acting on the car. The object's weight is a measure of gravitational force exerted on the object. So that's the weight. And we would say gravity. We would actually label it as gravity. I would say this is the force of gravity, and this is the force of the normal. So in my diagrams, I would use lowercase letters to describe the force. If the vector sum of the forces on an object is not 0, then the forces are unbalanced. The object will change its motion in the direction of this net force. So if I built my paper tower and I put this paper here, and this net force over here, I'm not sure exactly the best way to draw this, is not balanced with this net force here pushing against it, then the object's motion is going to change. It's not going to stay at rest. It's going to change that way. So in these scenarios, the box starting from rest, what forces are acting on the box, and what direction is the net force, and how will the box change its motion in response? So in this scenario, the normal force is pushing upwards, while gravitational force is pushing downwards. Let's see now. Is there a spring force or a tension force? Normal force or gravity? If this box is experiencing a pull because of its hanging from suspended from an object, we would say that's the tension. Sorry, because my pen doesn't let me write the E correctly. And it's still experiencing gravity, which is the force of the object's weight as the earth pulls it down. And in this one, we see the box resting on a spring. So there is a spring force. Boop. And we see the force that's compressing the spring is the weight of the object caused by the force of gravity. So to determine net force, we want to consider what are all the total forces acting on the box. So there's multiple forces acting on an object, and we call this a free body diagram. When we analyze all the forces acting on a simple object, and when we use free body diagrams, we can use simple shapes to represent complicated shapes. Like squares could represent anything like a car. And what we do is use vector addition to combine the forces, or they can be represented mathematically. So if I know the magnitude of this arrow and the magnitude of the friction force, if the force of gravity is like stronger, then I might say that this box will start getting pulled in the downwards direction, down the ramp. That would be its motion. If these force vectors are equal, the box will stay at rest, and it won't move. It'll just stay on the table. Now, if we apply a force to the box, maybe we put an applied force this way, it could start pushing, it would start moving that way. So the thing that's causing the box to be at rest, if it's on this table, is friction. So whenever an object is pushed or pulled across another object, like the box sliding down the ramp, friction always results. And the vector sum of the forces of all of these small points of contact pushing against each other, so this is pushing, it's all adding up to the total force the object is experiencing to resist the motion. So we say that's called static friction. When the box slides, it experiences kinetic friction, and that's what can cause heat energy to get released when objects experience extreme kinetic friction. So if it starts sliding, this energy is kinetic.